then I need now my second presentation. This is getting a little bit more colorful now. So the first part, the lightning talk, was about, let's say, the gray optics, and now we're coming to the colorful world, the DWDM part. I'm pretty sure every one of you already made that experience, having a great conversation, a technical conversation with someone, and then afterwards you figure out, hey, that's an interesting topic, I want to know more about it, and then you start to research it, and then you figure out, wow, that's tough, a tough topic. Yeah. Actually, this happened to me last year at the RIPE meeting in Lisbon. I met Blake Willis, and some of you might know Blake Willis. He can be really intense. The conversation can be really long and intense, and we had a really great conversation on the social about 400 gig coherent transmission, 800 gig, and about the balanced receiver and the colorless. Those two acronyms were always in that conversation, and I went back and said, hey, what is so special about colorless when it comes to coherent detection? What is so special about the balanced receiver? Why is it important, especially for you as a network operator, when you design your DWDM network in the 400 gig area? So we sat together internally, had a conversation, and yeah, it took us a while to understand and fiddle all the bits and pieces together, and that's my presentation today. So you basically get the result, what we figured out. It's called Channelmania, and where we're getting to 1.6 terabit for a DWDM network. So in general, this talk is separated in two sections. When we look into a transceiver, we also have two sections in there, the transmitter and the receiver. Together they get the artificial world of transceiver. And these two golden boxes were gonna play a major role now in that talk. And for sure, the digital signal processor who does all the math, all the magic. And you will see later on what the DSP will do. And you will see there is some history back to your high school time. So yeah, you will see it, how to do the math there. First of all, on the laser side, lasers have been around for a really long period of time, started in the early 50s. They were big boxes, needed a lot of power and especially a lot of cooling. They were not operational at room temperature. They needed liquid nitrogen to get them stabilized, basically, the frequency. And for us in the telecommunication part, the 70s were basically the first lasers which we could use at room temperature, and from there on its history, we made them smaller, we made them more efficient, that we can run today 400 gig, 800 gig, and so on. So what about the laser source in general? Well, I have a comparison here of 4 different laser sources. Also, it's a little bit the evolution of transmission in telecommunication. On the top left corner, that's a typical spectrum of an LED. It has a broad line width of 100 nanometers, so it's a really broad line width. And with the 10 gig area, the Fabry-Perot laser came into place with only just 10 nanometers, with very characteristic those 2 peaks on the side. And it's in the blue rectangle. And then towards the 100 gig, the distributed feedback laser is really a sharp peak already with 1 nanometer, or let's talk in frequency, 125 gigahertz. But still not sufficient when we want to do coherent. We need something a little bit more precise, a more peak, I would say, and the external cavity laser, the ECL, gets down to 1 megahertz of just a peak of our line width, which is really, 1,250 times narrower compared with the DFB. Now, when we want to increase bandwidth in general on the fiber, there are 2 approaches. So in general, we have our optical carrier in the middle, and then around the optical carrier, we have the optical bandwidth, or where the information content is encoded into that signal. So that's what you're going to see in the top one. Now, in the past, so far in the traditional 1 gig and 10 gig DWDM networks, we run for the approach to separate the different frequencies by colors. We said CWDM or DWDM to separate them with filters. Then we said, okay, the red and the green color we separated. We have a filter who gives a defined slot only for 1 color. But the drawback there is lost spectrum, because two filters next to each other, there's always an overlap, and we can't use that spectrum at all. This is the spectrum which is reserved for the filters. They need this, otherwise they can't distinguish between the two neighboring channels. So then, to simplify it, well, we just use one channel and broaden the spectrum and put way more information into a broader spectrum. For sure, we have less channels then, but within one channel, there's way more information. That's the right example with the broad spectrum. Okay, this was the easy part. When we did that research, it became a little bit of brain fry, but we also figured out, hey, there is more in there. So let's look a little bit on the receiver side. The receiver in general is a simple photodiode. You see it in the middle. The photodiode is an electronic component. It works straightforward. When there is light on the photodiode, it's opening up, current is going through, we get a 1. When there is no light, the diode closes, we get a 0, and that's all the magic we do. So we get 0 and 1s. Now, light is not light. In the traditional approach with on-off keying, you skip basically all the information which is inside of the light, which is part of coherent, it covers all, which is the phase information or the frequency, because the photodiode can't figure that out. It basically just sees there is light or there is no light, but showing the 3 pulses on the left side, it doesn't matter if the phase or the frequency does change between our 2 stages of 0 and 1, it's all the same. It's always either 0 or 1. So we need a little bit more to do coherent detection. And for that, I'm referring to the constellation diagram, the 16 QAM, which is a well-known modulation scheme in coherent detection. So each super constellation point, which you can see here on the left side, these are 16 in total, and each constellation point does encode 4 bits and per symbol. That's how we define it. And the interesting part now is when we pick out one constellation point in precise and say, hey, where is it located within that diagram? And we need something like a vector, or here the amplitude or the argument. And the amplitude is our vector, and this vector has a distance and also an angle. And with that, we can do the math to calculate where this constellation point belongs to. The alternative, when we go back to our high school math class, it's a rectangle triangular. We can also say, well, we have a x and y component and can do the math there. Or in this example, it's the quadrature or the in-phase component. And with that, the DSP can do the math and calculate the exact position of that dot. And that's important to remember. Okay, now to the receiver in general. As I said at the beginning, there is this word about of a balanced receiver. Let's start how such a receiver in general look like. We have a really critical component inside of a coherent receiver. That's our optical coupler. An optical coupler is a very simple device. It has 2 input interfaces and 2 output. And what it does, it takes the 2 incoming signals, combines it, couples it, and brings both signals combined on the 2 output ports. That's what an optical coupler does. And on a single-ended receiver, what we see here is on the incoming side or on the input ports, we have our optical carrier with the information content. That's the orange path. And we have a second path, the local oscillator. It's a second light source, which is similar on the same frequency like the optical carrier, and we combine it. And this coupler has a great thing. When we combine 2 frequencies, we take it off, we can deduct it. And we can down convert then our signal on a way lower level, because on the light level with coherent, we talk about terahertz in frequency, but this is not detectable at all. So we want to get it down converted, and the coupler does this for us. So the down converted signal, again, combined with the optical carrier and the local oscillator in the coupler, is detected by the photodiode on a single-ended solution. Now, on the second approach with the balanced receiver, on the input ports, it looks pretty much the same. Still there, the local oscillator and the optical carrier with the information content, and the coupler combines. But now we have on the output ports 2 receiving diodes, and both of them get the signal. And the down-converted signal is still there, but it gained way more amplitude because the coupler has an interesting thing what's happening in there. There is a phase shift happening on the cross ports. So the local oscillator phase on the left bottom port is phase shifted by 90 degrees to the right top port, and the same occurs to the optical carrier. It's also phase shifted to the right bottom port. So in total, they are phase shifted by 180 degrees. And when we look at 2 waves now, when they are both at the same time at a peak, when they overlap, what's happening? They double themselves. They gain more power, more strength. And that's also happening with the coupler on those 2 diodes. So our down-converted signal is way stronger, and we have more output and less noise, which is very helpful to detect. And with that, we move on, because now we at least have a down-converted signal, which is helpful, but we still have the phase information. The INQ component, which I showed previously on the constellation diagram to identify on where this dot in the constellation diagram belongs to. So we have to distinguish between the INQ component, and it's quite straightforward. The only thing what we do, so we have 2 couplers now, instead of 1, 2 couplers having each 2 diodes. And the only thing what we do is we phase shift again the local oscillator by 90 degrees. So, and feed this into the lower coupler, and we get the Q component, and the top one is not phase shifted by 90 degrees. We get the I component. And instead of having 2 for the diodes, we have now 4 of them. And to summarize this, because coherent is not only about phase information, we also have polarization information, similar like what you use when you wear sunglasses. They take out some polarization directions of the light. The same applies to a coherent receiver here. We take the signal and we use a polarization beam splitter and a rotator and separate it into 2 polarization directions and feed it into an optical hybrid, basically this construct which we have built now with the couplers. We call this the optical hybrid. So we have polarization direction 1 and 2, and in total 8 photodiodes are operational now to detect the phase information, the polarization, and so on. And that's our balanced receiver. Well, and knowing this now, we cannot only build, we can actually build now a rocket, and we can do something with that. Let's have a look at it. In general, coherent detection, when we look now on the where we are coming from 400 gig with 16 QAM, we need a rough bandwidth of 75 gigahertz. And as I showed at the beginning, when we want to increase the overall bandwidth to 800 gig or even 1.6 terabit, we basically just broaden our spectrum and we take more optical bandwidth. So for 800 gig, still with 16 QAM, it's 150 gigahertz. And for 1.6 terabit, it's going to be a roughly 300 gigahertz, sticking to the same modulation. They all have in common, they all fit into a filter when we say, well, the filter is roughly 400 gigahertz wide. Each channel has 400 gigahertz. They all fit perfectly in there into a single channel. When we look a little bit deeper, this is more comparison how the traditional approach would look like with 50 gigahertz DWDM filters. The great thing on such a 400 gigahertz DWDM filter is, well, we have up to 12 channels on the C-band, only looking at the C-band. And when we do the math with 1.6 terabit per 400 gigahertz filter slot or filtered channel, we get roughly 15 terabit of bandwidth on a single pair of fiber, which is quite a lot. An additional advantage is also the less channels we have in total, we have less insertion loss on the multiplexer, comparing it, for example, with a 96 AWG 50 gigahertz multiplex, they were rated up to 6 or 7 dB, which is quite a lot. And you have to compensate it with amplification at the end of the day. On the other side, a 12-port 400 gigahertz is roughly at 2 dB, which is quite helpful. Now, coming back to that down-converted signal, because this is not the whole story yet, about the balanced receiver and also about the colorless thing. When the coupler combines the two signals and we do the down conversion, so the local oscillator and the optical carrier are combined, and that's the great thing there. They eliminate themselves and only the optical bandwidth is left over. Something's happening in there, and the first approach is, or the way is called heterodyne, when the local oscillator is not exactly on the same frequency like the optical carrier. In this example, we are roughly 5 nanometers away, or there's a difference of 5 nanometers of those two wavelengths, or in frequency, it's roughly 622 gigahertz, the offset there. Now, also another effect happens in the coupler, and that's actually a drawback. We also get a mirror frequency on the negative path, and we don't want that mirror frequency, or it could influence our neighboring channel when there is a desired signal as well. So this mirror frequency makes more trouble. And on the other side, when you run on an intermediate frequency of 622 gigahertz, this is not impossible to detect today, but it's very expensive to do so, and especially in a small scale on a transceiver itself, running a receiver on 622 gigahertz. So the other way then to say is, well, we have to get the local oscillator on the same frequency like the optical carrier, because then when we do the math and deduct those two numbers, we get an intermediate frequency of 0 gigahertz, which would be the homodyne way, which would be awesome. In theory, yes. In practice, again, not feasible, because the components which are involved there, an optical phase lock loop, are expensive and also in terms of size not buildable into a transceiver. So when we combine this together, the solution is actually to do the intradyne detection, get the local oscillator as close as possible to the optical carrier, as far as we can get, have some offset there. They are coupled. The mirror frequency is not an issue because we are still within our optical band of, let's say here in this example, of 75 gigahertz. So the mirror frequency does not influence a neighboring channel, which is good. And then when we down convert it, the intermediate frequency in this example is roughly at 5 gigahertz. And all the folks doing some electronics, building a receiver with running on a frequency of an electronical receiver on 5 gigahertz is quite simple to do so. And even more, what you can do is you can tune that receiver on the electrical path. So you can either tell that receiver, hey, you're running now at 4.7 gigahertz or even at 5.2 gigahertz. So you can actually tune in the receiver to the frequency which he needs to see, or in other words, the signal which he needs to detect or discard. And that's basically the colorless part. You can tune now the receiver that he sees only the desired signal, what he's gonna want or need to see. And that's the new thing on the coherent side. So not only tuning the laser, the source, but we tune now the receiver as well. And with that, yes, we can build a rocket, and we can even go further. We can go to the moon, or there is way more behind the moon. And let's have a look at it. We call this our DIY super channel. And when we go back to those 400 gigahertz filters now, and now what you see there is there are 4 peaks in there. And each peak, or each wave, is carrying not 400 gigabit, so there are in total 4 times 400 gigabit in there in a single filter channel. So we don't separate the colors by the filter. This is not needed because our receiver, he can tune into the appropriate color. On the left side still, this would be the traditional approach where you have to filter each single color, but for the coherent one, you don't have to. And that's also what we discussed with Blake. He tried that, and he was quite successful running their 4 different waves in one single filter and separate them with a spacing of roughly 100 gigahertz. And behind that filter, what he did, he just placed a splitter known from the PON network. It's a cheap, simple component. And what happens now is when you look on the left side, this is all your optical carriers coming in. They are separated by the multiplexer. And then when they hit the splitter, on all 4 legs, all 4 signals are going to the receivers. But only the blue receiver grabs the blue signal because he's tuned into the blue color. This is the colorless part. The green receiver is tuned to the green color, and the yellow and the red, so on. And now you can imagine what you could also do is, well, when the blue receiver is failing, that's one router of yours, and it's failing, what you can do is you can tune the green receiver into that blue path because he already gets the optical signal, and now only on the electronic side you have to tune in the receiver to get that blue signal, and here we go, your link is still there. It doesn't matter what's happening on the left side on the source. And that's pretty amazing, so you don't have to rewire things, you don't have to use different ports, it's all done via that splitter combination because the receiver grabs the signal which is in 10 frame. For sure, as it's a kind of a PON network or PON style, on all legs, all the optical light levels are detectable, so you should only do this in your own network where you own the fiber, and you should know on which path, which frequency is operational and somehow in the background, otherwise you will mess it up. With that, I'm almost through. My finding here was, well, as I said before, there's way more behind the moon, there's a whole universe, and it's also quite helpful now when you know as a technical person how this coherent detection works. You can rethink the DWDM design you have done so far in the last couple of years, especially now in the area with IP over DWDM, where the transmission part becomes more and more part of the layer 2, layer 3 equipment. And just one example here for me is also the matrix which you get out of those modules. There is a difference between the optical light level, that's actually the light level which is coming in, and also the optical receive level, and that's actually the level where the receiver is tuned in. And when, for example, those figures differ, then you might be on the wrong frequency and you get the wrong signal. That's just an operational point of view. A big finding for me as well was forget about thinking in nanometers and channel numbers because you will screw it up anyway. ITU did a bad job there with their channel numbers, and Cisco added something as well. Terahertz and gigahertz is the truth. It's simple to calculate with them, and it's quite helpful. So think in terahertz and gigahertz and get rid of the nanometers and channel numbers. And I also got that question from the industry, okay, who is doing something broader than 200, 300, 400 gigahertz in the filter area, because we are not a filter company. And I looked a little bit around, and I was quite lucky finding Adtran did a new product at the beginning of this year, I think. They launched it, or last year, end of last year. They at least went to 300 gigahertz in their FSP 3000 with 8 channels, something like this. And there's also some amplification in there. It's a nice 1U box what they did there. So they're getting there that the filters are getting more broader. And a little bit the out view, well, what's happening on a terabit scale. Yes, the next big thing is going to be the 12.8 terabit, called also the XPO, and that's also what Michael previously demoed or not showed, was talking about. It's all about liquid cooling. So the liquid cooling is happening in the transceivers in the near future. There will be 2 inlets next to the connector where you have the liquid going in and the liquid going out, with the nice benefit, having 12.8 terabit. Okay, so I'm quite happy for the social tonight. Let's see what discussions will arise there. And before I leave the stage and Inga will take over, I'm almost good. I have one more thing. We just launched the FLEXOPTIX Inc. in the US, in California. Since 10 days we are live in close to San Francisco airport. So yeah, we are happy to support you in the US as well. Thank you.
Thank you. And thank you, Thomas, and congratulations on the launch of FLEXOPTIX Inc.
Thank you. Thank you. Yeah, that's our new baby.